Okay, so let me begin. So I'm going to be talking about a robust version of Hegedus's lemma, which is a nice lemma in combinatorics with applications to theoretical computer science. This lemma deals with polynomial functions defined over the hypercube. The n-dimensional hypercube, just to recall, is the set of all strings in 0, 1 to the n, and this is how I'm going to depict the n-dimensional hypercube. So at the bottom, I have the string of Hamming weight 0, the all 0 string, and then I have strings of weight 1, weight 2, etc., all the way to the top where I have the all 1 string, which is a string of Hamming weight n. Okay, and in this talk, we're interested in functions mapping the hypercube to some underlying base field f. Okay, and so it's not hard to see because 0, 1 to the n is a finite set that any such function can actually be represented by a polynomial, by a multivariate polynomial. Okay, and this follows from straightforward interpolation. So in fact, it's a standard fact that any such function can be written as a polynomial of degree at most n. Okay, so polynomial functions of the hypercube are really all functions over the hypercube. Nevertheless, it's very interesting mathematically to understand those functions over the hypercube that can be written as low degree polynomials. Okay, so the focus of this talk is on understanding some combinatorial / algebraic properties of low degree polynomials over 0, 1 to the n. Okay, and apart from being a nice mathematical question or a family of questions, such questions also have many applications in theoretical computer science. Okay, so let me just give you a very selected list of such applications. So such investigations are useful, for example, in understanding and proving results of complexity theory, specifically in circuit lower bounds and in the randomization. They're useful in devising algorithms in learning theory. And more recently, they've also found applications in devising devising algorithms for various combinatorial problems. Okay. And so such statements can be extremely useful in areas of theoretical computer science. And Hegedus's lemma is one such statement that has found applications. Okay. So what does Hegedus's lemma say? So at a high level, Hegedus's lemma talks about how well low degree polynomials can distinguish between different Hamming weights in the hypercube. Okay. So let's take the n-dimensional hypercube and fix two parameters k and q. Okay, so and let's look at points of Hamming weight k, so points with exactly k many ones, and points of Hamming weight k plus q, so points with k plus q many ones. So let me say that a polynomial distinguishes between these two levels or these two weights if it vanishes at all points of Hamming weight k and does not vanish at any point of Hamming weight k plus q. Okay, so then I say that a polynomial R distinguishes between these two weights. Okay, and the question is, what's the lowest degree polynomial that can distinguish between weights k and q plus q? Okay. And the answer, somewhat surprisingly, maybe depends on the underlying field f. Okay, so if f is a field of characteristic 0, for example, the rational numbers, so it's very easy to come up with such a polynomial. So, for example, take this polynomial, just sum all the input variables and subtract off k. So clearly, this vanishes at all points of Hamming weight k, but does not vanish at any point of Hamming weight k plus q. Okay, so more generally, this construction also works over fields of positive characteristic p, as long as this parameter p does not divide the parameter q. Okay, so as long as p does not divide q, again, the same polynomial vanishes at all points of Hamming weight k, but does not vanish at any point of Hamming weight k plus q. Okay, so this question is really interesting when the characteristic the underlying field has positive characteristic p, which divides the parameter q. Okay, more specifically, this question really gets interesting when q is a power of p. Okay, so let's look at this scenario. So assume q is a power of p, and now the construction from the previous slide no longer works. So what does work? Well, there is actually a construction that works over all fields. Okay, and so I'm going to describe that construction for you now. And so it's not directly relevant for what we're going to do, but it's still good to see it. Okay, so how do I come up with a polynomial that vanishes at all points of weight k, but does not vanish at any point of weight k plus q? Well, for definiteness, let's say that the polynomial R is going to take the value 0 at points of weight k and take the value 1 at points of weight k plus q. Okay. Note that the constraints on R are symmetric constraints. They only depend on the Hamming weight of the underlying input. Okay, and in such a scenario, it's very natural to construct R in a specific way. So more specifically, what I want to do is I want to come up with a univariate polynomial. This univariate polynomial only depends on the Hamming weight of the underlying input, so that the univariate polynomial vanishes at weight k and does not vanish at weight k plus q. And then I plug in summation xi, which is the Hamming weight of the underlying input x, into this polynomial to construct my overall polynomial R. Okay. And so this is a construction that actually works over the rational numbers, for example. But if it so happens that the univariate polynomial R actually has integer coefficients, then I can take this same polynomial and drop all of its coefficients modulo p to get a construction that works over any field. Okay. So once again, I want to come up with a univariate polynomial R with integer coefficients that vanishes at Hamming weight k and does not vanish at Hamming weight k plus q. So it does R1 of k is 0 and R1 of k plus q is 1. Yeah. And then I plug in the Hamming weight of the underlying input into R1 to construct my polynomial R. And assuming R1 had integer coefficients, I could drop the entire thing mod p to get a construction over my field of characteristic p. Okay. And so now the question is, what is the lowest degree polynomial R1 which has this property? And so using some ideas, one can actually show that degree q is sufficient for this property. Okay. So this gives a polynomial of degree q that can distinguish between Hamming weight k and k plus q over any field. Okay. And what Hegedus's lemma tells us is that this is tight. Okay. So Hegedus's lemma actually says that this construction cannot be improved. So more formally, over a field of characteristic p with q being a power of p, we actually can show that, so Hegedus's lemma shows that any polynomial R that distinguishes between weight k and k plus q actually has degree at least q. Okay, so this is a pretty nice lemma, and Hegedus proved this lemma in 2010 in order to prove a nice combinatorial result about set systems. And his proof too was somewhat involved. It used a Grobner basis computation from an earlier result, also due to Hegedus. More recently, I and independently alone found elementary proofs of this lemma. Okay, so by now this lemma actually has a pretty short proof, pretty short and elementary proof. Okay, and not just that, it also has applications in theoretical computer science. So in 2018, Alon, Kumar, and Wolf used this lemma in order to improve multilinear algebraic circuit lower bounds. And sometime last year, Rubesh et al. Used this lemma in order to prove some depth 2 threshold circuit lower bounds. Okay, so there's a nice lemma of polynomial functions, and it has already seen some applications in circuit complexity. Okay, so in this result, we are looking to prove, we're trying to prove a kind of a strengthening of this lemma, more specifically a robust version of this lemma. So what does that mean? So the Hegedus lemma deals with polynomial functions that exactly distinguish between Hamming weights k and k plus q. And in this robust version, we sort of relaxed this condition a little bit and just asked for polynomials that approximately distinguish between weights k and k plus q. Okay, so more formally, let me say that a polynomial R approximately distinguishes between weights k and k plus q if it vanishes at most points of weight k and does not vanish at any point, does not vanish at most points of weight k plus q. Okay, and this most is governed by a parameter epsilon. Okay, and the question is again, what's the lowest degree polynomial that does this? And once again, the interesting case for this lemma is when the characteristic of the underlying field is some positive number p and q is a power of p. Okay, and so now one can ask, is it possible to still hope for the same kind of lower bound, a lower bound of q? Okay, and the answer is no, because of course the bound has to depend on epsilon in some way. But at a kind of a slightly more deeper level, there's a qualitatively different construction that can approximately distinguish between two Hamming weights. Okay, so what is this construction? Well, the construction is very simple. It's just based on sampling. Okay, so in order to describe it, let me instantiate k and q to specific values. So assume that k is a number slightly smaller than n by 2, so say 0.49 times n, and k plus q is slightly bigger than n by 2, say 0.51 times n. These exact setting of parameters are not important here. All that matters is that the separation between the two weights is a constant times n. Okay. So in this situation, what's a really low degree polynomial that can distinguish between these two levels? It's very simple. Just take the polynomial R to be the majority vote of the first t input bits. Okay. So just take the first t among the n inputs, x1 to xt, and if more of them are 1, then output 1, and if more of them are 0, then output 0. Okay. So just take the majority vote in the first t input bits. Now, why does this work? Well, the answer is simply because of Chernoff bounds, right? So on a random input of Hamming weight 0.49 times n, Chernoff bounds tell you that with high probability, the majority of the first t inputs is going to be 0 with high probability. And similarly, on a random input of weight 0.51 times n, again, Chernoff bounds tell you that the majority of the first t inputs is going to be 1 with high probability. Okay. So in order to actually get the error probability to be less than epsilon, we need t to be something like log 1 by epsilon. And at that point, Chernoff bounds tell you that these do approximately distinguish between weights k and k plus q distance. Okay, so this is a very different construction from the interpolation construction on the previous slide. And so what's the degree of this polynomial? Well, as I mentioned some time ago, any Boolean function that depends on n inputs has degree at most n. So this is a Boolean function that depends just on t inputs. So it has degree only t. So this is a polynomial of degree t, which is something like log 1 by epsilon. Okay. And so you notice that there is no dependence on the degree on this parameter q whatsoever. So when q is something like a constant times n and epsilon is a constant independent of n, this is actually a much lower degree. Okay. But on the other hand, as q gets smaller and smaller, you would imagine that it gets harder and harder to distinguish between these two weights via sampling. Okay, so indeed the degree of this polynomial gets worse and worse. And at some point, you could imagine that the degree via the sampling construction is actually worse than the degree we obtain via straightforward interpolation. Okay, and indeed this does happen. And at that point, you can ask, is there a third construction that does better than both of them? Is there a completely different construction? Okay, and the main result of this paper is that that's not the case. Okay. So what we are able to show is that for approximately distinguishing between two different weights in the n-dimensional hypercube, the best thing you can do is what is the best among the sampling bound, roughly described on the last slide, and the straightforward interpolation bound, which is q. Okay, and so this is the main result of the paper, and so it's a minimum of two bounds, but in the paper it's stated in a regime where actually the two bounds are equal, and that's when actually this lemma is at its most useful. So let me give a version of that statement here. So imagine, for example, that k is set so that k is like n by 2 minus something like square root n. So take epsilon to be a constant for the slide. And so assume that k is something like n by 2 minus square root n and k plus q is something like n by 2 plus square root n. So in this regime, one can actually show that both the sampling bound and q give the same thing. Okay. And both of them yield a lower bound or something, and the minimum of the two yields a lower bound of something like square root. Okay, so our main result implies that in this regime of parameters, the degree of any polynomial r that approximately distinguishes between weight k and k plus q is in fact degree root n. Okay, so that's the main result of this paper. So I hope the statement was reasonably clear. And so I want to describe now a few applications that we can use this statement for. Okay, so so the robust Hegedus lemma approved in the last slide also has a few nice applications that I want to describe to you. So the first of these is for proving degree lower bounds for the coin problem. Okay, so the coin problem at a high level is a problem of distinguishing between two coins, one of which is slightly biased towards heads and the other which is slightly biased towards tails. Okay, so as a computational problem, this is pretty fundamental, and it's actually been studied from a circuit complexity point of view by many previous works. Yeah, and recently in a previous work, we tried to understand the minimum degree required to actually solve this coin problem, distinguish between coins of two different biases. And in this work, we're actually able to give optimal degree lower bounds for this problem, optimal polynomial degree lower bounds for this problem via the robust Hegedus lemma. So that's one application. The second application is to approximating Boolean functions by polynomials. Okay, so in a kind of a classical work of Rasberov, he introduced a notion of polynomial approximation that now goes by the name of probabilistic degree. Yeah, and using the fact that certain Boolean functions cannot be approximated by low degree polynomials, Rasberov was able to show strong circuit lower bounds for computing certain symmetric Boolean functions. And soon after, Rasberov's polynomial degree lower bounds were strengthened by Smolensky. And now strengthening Smolensky's lower bounds further, what we are able to do as a corollary to the robust Hegedus lemma is to give optimal probabilistic degree lower bounds for all symmetric functions. Okay, so by given any symmetric function, so any Boolean function that depends on only the Hamming weight of the underlying input, we now understand up to a constant factor what its probabilistic degree is over any field of positive characteristics. So that's another result. And the third result is actually a purely combinatorial result. So if you recall, I mentioned that Hegedus was able to use his lemma in order to prove an extremal result about set systems. And what we are able to do is now use the robust version of his lemma to prove a robust version of his result for set systems. Okay, so that's the third result. So this lemma has two nice applications to theoretical computer science and one nice application to combinatorials. Okay, so these are some nice applications. So I want to end this talk by giving you some ideas behind the proof of this lemma. Okay, so how does one go about proving it? And again, let me just recall this lemma. So once again, we want to distinguish approximately between two different Hamming weights. And just to simplify the statement of the lemma, I've taken epsilon to be a constant. So in this regime, what the lemma says is that you want to distinguish between Hamming weights n by 2 plus square root n and n by 2 minus square root n, where this difference is actually a power of the underlying characteristic p. Then the degree of such a polynomial that approximately distinguishes between these two levels must be at least a constant times square root n. Okay, so that's what the robust Hegedus lemma states. So I just want to point out a parallel between this lemma and a result that's already very well known in the computational complexity literature. It's a result of Smolensky. So what Smolensky showed was that any polynomial that approximates the majority function in a well-defined sense must have a degree at least root n. Okay, but if you look at his proof, he actually proves something slightly stronger. So what he shows is that if I take a polynomial r of x1 to xn, which vanishes at most points of Hamming weight at most n by 2, and is non-zero at most points of Hamming weight at least n by 2, greater than n by 2. Okay, so take any polynomial that vanishes at most points here and is non-zero at most points here, then the degree of such a polynomial must be at least a constant times root n. Okay, so that's Smolensky's theorem, and this is used for proving certain constant depth circular law models. And so you can see that at least in the face of it, our result is quite similar to Smolensky's result. And indeed, we view our result as a kind of a strengthening of Smolensky's result in some sense. Okay, and therefore it's not surprising that the proof of this lemma also proceeds along the lines of Smolensky's proof. Okay, so the main idea of the proof of this lemma is actually to run Smolensky's proof, but instead of running it over the entire hypercube, we run it only on certain levels of the hypercube. Okay, so we only run it on levels of the hypercube that are actually congruent to these interesting levels for us, modulo the number cube. Okay, so the idea of the proof is to sort of restrict Smolensky's lower bound proof to just the Hamming weights which are congruent to these numbers modulo q. Okay, and this in fact is where the characteristic of the underlying field comes in. Okay, so in order to be able to do this, we use the characteristic of the underlying field. So there is a kind of a classical result from the 1800s called Lucas's theorem, and what that states in suitable language for us is that there is a low degree polynomial, a polynomial of degree at most q, which has the property that q is non-zero only at points whose Hamming weights are congruent to our interesting Hamming weights modulo q. Okay, so there's a polynomial q1 of degree at most q, so that q1 is non-zero only at points of Hamming weight congruent to these Hamming weights modulo q. Okay, and this is a kind of a technical, small technical fact that allows us to sort of restrict Smolensky's proof to points of Hamming weight at most q. The points of Hamming weight congruent to these weights modulo q. Okay, but nevertheless, even after this is done, it's not that Smolensky's proof immediately goes through. One has to work with the right version of Smolensky's proof, and there's still some more ideas involved. In particular, we also use some extremal results about Zariski closures of finite subsets of 0, 1 to n. So these are some nice combinatorial / algebraic combinatorial facts, which have actually also been used previously in this literature. So I'm not going to describe them here, but they're actually pretty interesting combinatorial statements that we use in order to prove this. So I encourage you to look at the paper if you're interested. Okay, and that's all I wanted to say about the proof of this. So let me summarize. I told you about this nice lemma by Hegedus from the combinatorics literature, which has nice applications already to theoretical computer science. We formulated a robust version of this lemma and proved it along the lines of Smolensky's proof, but augmented with a few new ideas. Okay, and this lemma has many applications to polynomial approximation questions already in complexity theory, and also one nice application to combinatorics. But I would really like to see other applications of this lemma because I think it's a pretty nice statement. Okay, and that's all I had to say. Thank you.